In the AI models we have worked on so far, there are various hyperparameters that need to be determined. In this video, we will explore how to determine these hyperparameters and take a look at the coding file. Hyperparameters are variables that control the learning process of an AI model, and they need to be specified before training the model. Hyperparameter optimization, also known as hyperparameter tuning, refers to the process of determining the optimal combination of hyperparameters that maximizes the performance of an AI model. There are several methods for hyperparameter optimization, including manual search, grid search, random search, and Bayesian optimization. Manual search is a method where the experimenter manually adjusts the hyperparameters based on their intuition or experience. It involves directly modifying the hyperparameters while observing the model's performance. However, it is challenging to determine if the chosen hyperparameter combination is optimal, as the interactions between hyperparameters are not considered. On the other hand, grid search is a method where hyperparameters with predefined ranges are tested in a systematic way by evaluating all possible combinations within those ranges. For example, if we have two hyperparameters with 3 values each, a grid search would evaluate a total of 9 combinations to find the one that yields the best performance. In grid search, if the range or number of hyperparameters is large, it can significantly increase the computational workload. In such cases, the random search method can be used, where combinations are randomly selected and evaluated to find the combination that yields the highest performance. Unlike grid search, random search does not test all possible combinations, so it cannot guarantee the best performance. However, it has the advantage of achieving relatively good performance in a shorter amount of time. By randomly sampling different combinations, it explores a broader range of hyperparameter values, potentially discovering unconventional yet effective configurations. Now let's discuss Bayesian optimization, another method for hyperparameter optimization. Unlike other hyperparameter search methods, it is based on algorithms. Bayesian optimization is a method of searching for optimal values with prior information. It can be compared to the efficient process of drilling for oil, where randomly selecting drilling locations may not be as effective as analyzing the results of drilling in specific locations and using that information to determine the next drilling location. Similarly, Bayesian optimization narrows down the search space for optimal solutions based on previously explored results. The Bayesian algorithm consists of 2 main components, the surrogate function and the acquisition function. The surrogate function, often based on Gaussian processes, estimates the objective function using the available data collected so far. It creates a probabilistic model that approximates the behavior of the objective function based on the observed data points. On the other hand, the acquisition function guides the search for the next hyperparameter configuration to evaluate. It suggests the most promising input values that are likely to result in better performance. Let's briefly look at the process of Bayesian optimization. First, let's assume the yellow line represents an unknown objective function called the black box function. Initially, we randomly sample hyperparameter configurations and observe their results. Based on the observed values, the surrogate model estimates the optimal function represented by the blue line. And the acquisition function recommends the next set of hyperparameter combinations to be observed, which is marked in asterisk. Then, the surrogate model updates and refines the estimation of the optimal function. This process is repeated iteratively, with the acquisition function guiding the selection of hyperparameter configurations to explore. As the iterations progress, the algorithm moves closer to the true objective function, eventually identifying hyperparameter values that yield better performance. Next, let's examine the coding file that uses the support vector machine algorithm to create a model for classifying the iris dataset, and we'll search for the hyperparameters of the support vector machine using both grid search and Bayesian optimization methods. To perform this coding, we need to import libraries such as NumPy, Pandas, and TrainTest-Split. Additionally, we import the SVC library for support vector machine, as well as the min-max scalar library for normalization. We also import the necessary library for grid search. Then we load the Excel dataset and perform normalization. After that, we split the data into training and testing datasets using an 80-20 ratio, 80% for training and 20% for testing. After that, we load the support vector machine model. Here, we set the desired ranges for 3 hyperparameters: kernel, C, and gamma. These variable conditions are then linked to the grid search algorithm, which calculates the accuracy based on different combinations of hyperparameters. Next, using the best_params_ command, we can obtain the optimal values for each hyperparameter. The corresponding accuracy value obtained after applying these optimal values is also displayed. In this case, it shows that when the C value is set to 1, gamma is set to 1, and the kernel is set to RBF, the highest accuracy of 0.975 is achieved. Next, let's take a look at Bayesian optimization. Similar to the previous grid search, we import the same libraries and additional ones for the Bayesian algorithm and range configuration. After that, we load the Excel dataset and perform normalization. Then, we split the data into training and testing datasets with an 8:2 ratio. Next, we input the support vector machine model as the one to be optimized using Bayesian optimization. We also set the hyperparameters to be optimized and their respective ranges. Then, we train the model using the X training and Y training data and evaluate its accuracy. The result shows that the accuracy obtained with the training data is 100%, while the accuracy with the testing data is 0.967, indicating that the model correctly classified the iris species with an accuracy of 96.7%. In particular, by using the opt_best_params command, we can obtain the values for the hyperparameters that optimize the model.